Below 200 meters, about 656 feet, the ocean swallows every trace of light. The pressure is crushing, nearly 100 times the surface pressure. In these depths, some creatures turn transparent to vanish. Others unleash red bioluminescence, light that is invisible to most other animals. Every known rule of biology begins to fracture as we descend. It gets colder and stranger. The familiar world above becomes utterly irrelevant. Why does life down here look more like science fiction the deeper you go? The real answer begins where sunlight ends. At the ocean surface, light pours down in blinding sheets. Between 0 and 200 meters, approximately 650 feet, the water glows blue and alive. This is the sunlight zone, epipelagic, where every drop is charged with energy. At noon, a swimmer might see their shadow ripple across sand, while schools of fish flash silver just below. Pressure is gentle, 1 atmosphere at the surface, rising steadily with every meter, barely felt by creatures that dart and glide here. Photosynthesis rules this world. Phytoplankton drift in the upper layers, turning sunlight into oxygen and food. Sea turtles, tuna, and sharks chase prey in open water, relying on clear vision and speed. At 10 meters, 33 feet, 80% of sunlight remains. By 50 meters, 164 feet, just a third remains. At 100 meters, 328 feet, only 1/10 survives. The water cools, slipping from 20 degrees Celsius at the surface toward 4 degrees Celsius as you sink. Yet even at 150 meters, 492 feet, enough light filters through for life to hunt and hide by sight. This is the most familiar ocean, but the balance is fragile. Every 10 meters, the weight of water grows, 1 more atmosphere pressing in. At 200 meters, approximately 650 feet, pressure reaches 21 times surface pressure. Light drops to less than 1% of its surface power. The blue fades to green, then to gray. Shadows vanish. Below this line, the rules change. Eyes tuned for sunlight become useless. Muscles and bones begin to feel the squeeze. The surface world, with its color and noise, slips away. What was once open and bright becomes a threshold, a boundary between the known and the unknown. Here, at the sunlit edge, the deep sea begins to reveal its true nature. At 200 meters, the world changes. Sunlight fades to a dim, greenish haze. The surface is lost above, replaced by a slow-moving gloom that thickens with every meter. Here begins the twilight zone, the mesopelagic, stretching from 200 to 1,000 meters, or about 3,280 feet. Pressure mounts quickly, reaching 21 times the force at sea level and climbing to over 100 atmospheres by the lower edge. Temperature falls to 8 degrees Celsius, then slips toward 4 degrees Celsius. But it is the collapse of light that defines this realm. Less than 1% of the sun's energy survives the descent. By 300 meters, only a whisper remains, barely enough to read by if reading were possible in this liquid dusk. At 500 meters, sunlight is a rumor. 10 lux, the brightness of a candle across a room, is all that pierces the water. By 1,000 meters, sunlight is gone. The darkness is not total, but it is absolute in its intent. Vision, as we know it, fails. Eyes adapted for the surface become useless. Shadows disappear. There is no place to hide, yet nowhere to be seen. In this green-blue murk, the rules of survival are rewritten. Creatures here cannot rely on color or shadow to escape predators. Instead, many become nearly invisible. Their bodies lose pigment, tissues thin to glass. The glass squid and glass octopus float like phantoms, their organs suspended in clear jelly, their outlines nearly erased. This is not invisibility as a trick, but as a necessity. In a world where even a faint silhouette can mean death, transparency is the only true armor. Remotely operated vehicle cameras sweep their spotlights, and for a heartbeat, a ghostly form appears, then vanishes as the angle shifts. Scientists have struggled to capture these animals on film. In 2016, a glass octopus was recorded at 630 meters by Japan's Shinkai 6500 submersible. Even under careful lighting, it flickered between presence and absence, a living secret. The twilight zone is a boundary, not just of light, but of logic. Here, the familiar rules of the surface dissolve. The descent is not just physical. It is a passage into a world shaped by stealth, silence, and the relentless pressure of the deep. At 1,500 meters, nearly a mile below the surface, the ocean is a world of crushing silence and darkness. Here, the pressure reaches 150 times the pressure at the surface. No sunlight penetrates. Only the faint blue-green flashes of bioluminescence break the black. But one predator has found a way to see what no other can. The dragonfish, a slender ribbon of muscle and teeth, glides through the midnight zone with an advantage no other hunter possesses. Along its jaw, special organs called photophores pulse with a deep, red glow, invisible to almost every creature in the deep sea. This is not the blue light common in other bioluminescent animals. The dragonfish's secret weapon is red light, tuned between 690 and 710 nanometers. That wavelength vanishes within the first few meters of ocean water and is undetectable to most deep-sea eyes. In 2014, the National Oceanic and Atmospheric Administration mounted an expedition in the Gulf of Mexico. They sent the remotely operated vehicle Deep Discoverer to 1,500 meters. The dive leader watched as the vehicle's sensitive cameras picked up a flicker in the gloom. A dragonfish, jaws open, scanning the water with its private red searchlight. The control room fell, silent. The team realized they were witnessing a predator using a wavelength of light that rendered it invisible to its prey, like a sniper with night vision goggles. The dragonfish's eyes are uniquely adapted to see this red glow, granting it a hunting advantage in the perpetual night. Prey blind to red float unaware in the beam, moments from capture. This adaptation is more than a trick of color. At these depths, every advantage matters. The dragonfish's red bioluminescence lets it hunt in secret while other animals remain locked in a struggle to stay unseen. The evolutionary arms race has begun. In the deep sea, camouflage is not enough. Predators and prey push each other to stranger and more extreme adaptations, each step shaped by relentless darkness and the silent threat of being unseen. In the midnight zone, the rules of concealment reach their limit. Some fish here wear a cloak of darkness so complete it tricks even the brightest machines humans can send. In 2020, researchers from the Monterey Bay Aquarium Research Institute and the Smithsonian measured the skin of the fangtooth and several other deep-sea species. Their instruments showed a reflectance so low, just 0.05%, that the fish absorbed 99.5% of all light, making them the blackest known animals on Earth. The secret lies in their skin, layers of tightly packed melanosomes arranged to trap and scatter every stray photon. Even when a submersible's floodlights shine directly on them, these creatures appear as nothing but a pair of eyes and a row of teeth floating in a void. Stealth is not just for hiding from predators. In a world where a single glint can mean death, even a heartbeat of exposure is too much. The evolutionary arms race pushes camouflage to its extreme, but survival here demands more than invisibility. Finding a mate in the endless dark is almost impossible. For the anglerfish, the answer is fusion. Females grow large, with monstrous jaws and a glowing lure that dangles from their forehead. The males, by contrast, are tiny, sometimes just 1/40th the size of the female. When a male finds a female, he bites into her belly and never lets go. Over time, his body fuses with hers, blood vessels joining until he is nothing but a pair of gonads attached to her side, ready to fertilize her eggs whenever she is ready. This bizarre bond is not a quirk, but a solution to scarcity. In the vast emptiness, encounters are rare. Permanent attachment ensures that when two anglerfish meet, the chance to reproduce is never lost. Scientists have recorded this phenomenon on remotely operated vehicle dives, with footage showing the grotesque pairing, one massive luminous hunter and her tiny fused mate. Each adaptation in the midnight zone is a response to extremes: the pressure, the darkness, the hunger, the loneliness. As Dr. Paul Yancey once noted, even the chemistry of life bends here. Deep sea fish fill their bodies with TMAO, a molecule that stabilizes proteins against crushing pressure, a molecular armor that rises with every meter descended. In these depths, every solution is radical, every life a quiet act of defiance against the abyss. At 4,000 meters, the ocean floor stretches out in a cold, endless plain. Here, in the abyssal zone, life takes on shapes that seem impossible above. The pressure is more than 400 times the pressure we know on land. The temperature hovers near 2 degrees Celsius. Food is so scarce that most creatures drift in slow motion, conserving every bit of energy. Darkness is absolute. Silence settles like a blanket. Vast, flat mud plains roll away under a faint, pale light from distant bioluminescence. This is the abyssal world. Yet some animals here are giants. The giant isopod Bathynomus giganteus can reach lengths of up to 76 centimeters, about the size of a house cat. Deep amphipods like Hirondellea gigas have been found at similar sizes, dwarfing their shallow water relatives. This phenomenon, called deep-sea gigantism, defies easy explanation. One theory points to oxygen, because cold, deep waters hold more dissolved oxygen, which may allow larger bodies to function. Another theory focuses on metabolism. At near freezing temperatures, everything slows down. Growth takes years, but energy is stretched further, letting bodies grow bigger before reaching their limits. Then there are the rare feasts, whale falls, and sudden pulses of marine snow, when a bounty rains down from above and scavengers gorge themselves, growing rapidly in the aftermath. Scientists map oxygen levels across the abyss and track the size of animals collected by trawl and remotely operated vehicle. Patterns emerge, but the debate continues. Why do some species become giants while others remain tiny? Is it oxygen, temperature, or the luck of a sudden meal? The abyssal plain is a world of scarcity, yet in its mud, the largest scavengers on Earth wait for their chance. A whale dies in the open ocean. It begins a slow fall, tumbling through kilometers of water into absolute dark. Pressure builds, silence presses in. The surface feels 1,000,000 miles away. The ocean swallows the body until it crashes onto the abyssal plain, more than 4,000 meters deep, about 13,100 feet. Down here, pressure is 400 times surface pressure. Temperatures hover around 4 degrees Celsius. Light is gone. Only the faintest ghosts of bioluminescence remain. Silence rules the seabed. Within hours, scavengers appear. Hagfish slip in like living rags. Giant isopods emerge from the sediment. They swarm the carcass and strip flesh from bone. Amphipods mass in clouds. Sleeper sharks arrive and take their share. The initial feast can reduce soft tissue in a matter of months, in a place that usually waits in slow motion. Once the soft tissue is gone, a second phase begins. Worms and snails burrow into the sediment. They feed on the thick layer of fat and decaying tissue. Opportunists extract every last calorie. This stage can last for years, a long, grinding season of consumption. Life here moves in pulses, not continuous streams. Then comes the most haunting transformation. As bones settle into the mud, Osedax, the bone-eating worms, begin to bloom. These strange animals have no mouths or stomachs. Instead, they grow root-like tendrils that bore into bone and dissolve it, drawing out oil and protein. Sheets and clouds of osedax can cover a skeleton in weeks, turning white bone into a living reef. Hydrogen sulfide leaks from the decomposing skeleton. That chemical haze fuels bacteria and chemoautotrophs. Microbial mats flourish where nothing much lived before. The chemical energy supports communities for decades, long after the last scavenger has gone. Time-lapse cameras from the Monterey Bay Aquarium Research Institute, known as MBARI, captured this hidden spectacle on the abyssal plain. Expedition leader Bruce Robison said, "A corpse becomes a reef. A world rises from a fall. This happens unseen, far below." Those images revealed sudden, teeming life where we expected only emptiness. A whale fall is a momentary windfall in a world built on scarcity. Marine snow falls like ash for years, and then, in a single event, the deep sea explodes with abundance. In the dark, cold, high pressure of the abyss, a dead giant becomes a long-lasting oasis, a cascade of life born from a fall. What rules of life are bent here, where oil feeds microbial cities and worms turn bone into reef? What else waits buried in the mud for a rare chance to bloom? At 8,178 meters, over 26,800 feet down, the Mariana snailfish glides through water heavier than steel. Here in the Hadal trenches, the pressure reaches 1,093 atmospheres. Every square inch is squeezed by more than 16,000 pounds of force. Bones become a liability. The snailfish's skeleton is thin and flexible, its body soft as jelly. This soft form moves with the slow, relentless patience of the deep. Deep inside each cell, a compound called TMAO, trimethylamine N-oxide, builds up to extraordinary levels. TMAO acts as a molecular brace, locking proteins into shape and keeping them from unraveling under the weight of the deep. Laboratory measurements show that in the deepest snailfish, TMAO reaches a plateau near 400 millimoles per kilogram, so concentrated it nearly matches the saltiness of the surrounding seawater. Beyond this, the chemistry of life falters. No vertebrate has been found deeper. Dr. Mackenzie Geringer has spent years studying these limits. Her team's tissue samples pulled from baited traps and remotely operated vehicle dives confirm that snailfish are living at the very edge of what vertebrate bodies can endure. But even in this alien world, traces of humanity appear. In 2019, Victor Vescovo's submersible limiting factor touched down at Challenger Deep. The cameras caught a plastic bag drifting beside amphipods. Later, microplastic fibers were found inside the guts of trench-dwelling crustaceans. Scientists traced these fibers from the surface, carried by currents and marine snow, now woven into the food web of the planet's deepest creatures. The Hadal Zone is a frontier of biochemical possibility and a reminder that even the most remote life cannot escape our shadow. The questions grow heavier. How much farther can life adapt? And what happens when our debris outpaces evolution? Near the deepest trenches, where sunlight has never touched and pressure would crush a submarine, a different kind of fire burns. Here on the ocean floor, hydrothermal vents spew jets of water heated to over 350 degrees Celsius, hotter than a kitchen oven, yet surrounded by water just above freezing. These vents pump out hydrogen sulfide and methane, chemicals toxic to most surface life. Around these black chimneys, a thriving community gathers. Giant tube worms, vent shrimp, and ghostly white crabs cluster in the chemical haze. They owe their existence to bacteria that convert hydrogen sulfide and methane into energy, a process called chemosynthesis. Unlike every green plant on land, these bacteria need no sunlight. They build entire ecosystems from the chemistry of the Earth itself. On Earth, these vent worlds are rare oases. But the ingredients, rock, water, and heat, are not unique to our planet. In 2017, The Cassini spacecraft sampled plumes erupting from Saturn's moon Enceladus. The data revealed molecular hydrogen, methane, and tiny silica grains, signs of hot water reacting with rock, just like the deepest vents on Earth. Europa, a moon of Jupiter, hides a salty ocean beneath its icy crust. Models suggest its ocean too could touch a rocky floor with the energy and chemistry for hydrothermal vents. If life can thrive in utter darkness, feeding on hydrogen and methane, then perhaps the deep sea is not just an earthly secret. Perhaps in the black oceans of distant moons, alien creatures gather around their own chemical fires, waiting in the dark. Even now, more than 80% of our ocean remains unexplored, its trenches hiding forms of life that challenge the limits of biology. Each new dive uncovers creatures shaped by pressure, by absolute darkness, and by extremes we can barely imagine. As plastic fibers reach the Hadal zone, our mark descends with them. What evolves in the silence below, just beyond the reach of light or understanding?